So I want you to imagine trying to plan your morning commute to work, but you have this highly specific, bizarre form of amnesia.
Okay.
Like you literally cannot mentally picture the roads. You can't visualize the traffic building up at that one terrible intersection.
Oh, wow. Yeah, that would be a nightmare.
Right, and you can't simulate what a sudden downpour is going to do to the highway speeds. You literally cannot do it.
You wouldn't even be able to back out of your driveway.
Exactly. You'd be
Oh.
totally stuck. And the reason you usually navigate all of that effortlessly every single day is because you rely on a world model inside your head.
Right, a constant mental simulation of how physical reality actually works.
Exactly. And today we are doing a deep dive into how researchers are finally giving artificial intelligence that exact same ability. The ability to, basically dream or simulate the future.
Which is, I mean, it's historically been one of the highest hurdles in the entire field. Because biological brains, we just do this inherently.
We don't even think about it.
No, we predict the physical consequences of our actions without allocating any conscious thought to it at all. But engineering a computer system to do that, to autonomously build a working dynamic model of the world directly from high-dimensional visual data.
That's been incredibly brittle, right?
Extremely brittle, until now.
Right, which brings us to the core of today's deep dive. We are unpacking this brand new breakthrough research paper from a combined team at Mila, NYU, Samsung, and Brown University.
It's a powerhouse team.
It really is. And the architecture they've built is called LeWorldModel, or LeWM for short. The paper is titled Stable End-to-End Joint Embedding Predictive Architecture from Pixels.
It's a mouthful, but the implications are massive.
Yeah, so our mission today is to map out exactly how LeWM allows an AI to learn the fundamental laws of physics and predict future states from raw pixels.
And without cheating, which we'll get into.
Right, no cheating and without massive data center compute. They use this remarkably elegant mathematical constraint instead of just, throwing brute force compute at the problem.
Yeah, and for anyone listening who has ever tried to train their own world model or work with foundational vision architectures, you usually hit this massive solid wall when it comes to resource.
Oh, yeah. The compute budgets are usually staggering.
Exactly. We're generally talking about heavily parameterized foundational model, non-convex loss landscapes.
Meaning the math is just incredibly messy and unstable.
Right. Messy math that requires literal teams of researchers to manually tune the hyperparameters just to keep the training from completely collapsing.
Just babysitting the model.
Exactly. But this paper, it shifts that paradigm entirely. They actually prove that you can train a highly robust world model on a single standard GPU.
A single GPU.
Yeah, in just a matter of hours.
Which is wild. I mean, a single GPU fundamentally changes the economics of who gets to do this kind of research.
It democratizes the whole process.
It takes capabilities previously locked behind the doors of, massive tech conglomerates and puts them right on the desk of an independent researcher. But okay, before we can really appreciate the genius of what LeWM does, we need to talk about the trap that current AI falls into when it tries to predict the future.
Right, the failure modes. You really have to understand the current standard, which is the JPay.
The Joint Embedding Predictive Architecture.
Exactly. And look, the foundational concept of a JPay is actually really solid because older generative models, they wasted vast amounts of compute trying to predict the future pixel by pixel.
Which is just exhausting for a computer.
It is. Think about it. If an AI is tracking a moving car, predicting the exact pixel-level flutter of every single leaf on a tree in the background,
It's totally irrelevant.
right, it's computationally expensive and it has nothing to do with the actual dynamics of the scene. So JPEGs solve this by operating entirely in what we call a latent space.
Okay, so you're compressing the visual input, you squash it down into a lower dimensional manifold, filter out all that random stochastic noise like the leaves, and you just ask the AI to predict the next state within that compressed representation.
That's the intended mechanism, yes. You only model the features that actually matter. But, and this is a big but, you almost immediately run into this phenomenon called representation collapse.
The dreaded representation collapse.
It's the worst, because if the objective function simply tells the AI, hey, minimize the distance between your predicted future state and the actual future state,
It gets lazy.
it looks for the mathematical path of least resistance.
Yeah, when I was reading the source material on this, it immediately reminded me of like a lazy student taking a multiple choice test who figures out a loophole.
Oh, the all-sees strategy.
Exactly. Representation collapse is basically the AI realizing, wait a minute, if I just map every single incoming visual frame to the exact same constant number, say just an array of zeros,
Right.
then my prediction for the next frame is always going to perfectly match the actual next frame because the distance between 0 and 0 is 0.
It's a guaranteed perfect score.
Right. The network minimizes its loss to absolute 0, technically passing the test, without actually doing any work or learning a single thing about the physics of the environment.
You've hit on the exact vulnerability. The AI is technically succeeding at the math, but the representations become entirely useless for downstream planning. It's collapsed all that rich, complex visual reality into a single static point.
So how have previous models tried to stop the AI from cheating like this? Because I know representation collapse isn't a completely new problem.
No, it's been a thorn in the side of AI research for a while, but the previous workarounds, they've been either computationally brutal or incredibly brittle.
Give me an example.
Okay, take an architecture like PLDM. To force the network to maintain diverse representations and not just guess 0 every time, PLDM relies on a highly complex 7-term loss function.
7 terms?
Yeah. You have variance terms, covariance terms, reconstruction terms, all of them fighting against each other during training.
That sounds like an absolute nightmare for gradient descent. I mean, the loss landscape must just be chaotic.
It is incredibly unstable. You end up spending weeks running grid searches just to tune the hyperparameters. If even one of those 7 terms dominates, the whole training destabilizes.
Jeez.
So other architectures like DynoWM, they look at that tuning nightmare and say, no thanks. They take a completely different route.
What do?
They simply freeze a pre-trained foundation vision encoder. They lock the network's perceptual weights entirely so the representations literally cannot collapse.
Oh, I see. But wait, if you freeze the encoder, aren't you basically lobotomizing the network's ability to adapt?
Yes, that's the trade-off.
Because it can't learn task-specific visual features anymore. Its perception is permanently locked to whatever data set it was originally trained on. So you're sacrificing adaptability just to get mathematical stability.
Exactly. Which leaves the field stuck between 2 really bad options. Navigate a chaotic 7-term loss landscape, or freeze the network's perception and lose the ability to learn end-to-end.
Okay, so if a 7-term loss is a nightmare to tune and freezing the encoder limits learning, they obviously needed a cleaner mathematical whip to keep the AI from getting lazy, which leads us exactly to LeWM's secret weapon.
Right. The researchers behind LeWM throw out that messy 7-term approach completely. They utilize a streamlined 2-term objective.
Just 2 terms.
Just 2. The first term is your basic prediction loss, just minimizing the distance between the predicted state and the actual future state.
The one the AI tries to cheat on.
Right. But the second term is their novel anti-collapse regularizer. They call it SIGReg.
SIGReg.
Yeah, it stands for Sketched Isotropic Gaussian Regularizer.
Okay, let's unpack SIGReg because the name is a bit dense, but the math behind it is actually beautiful. How does it stop the network from collapsing into that lazy array of zeros?
Basically, SIGReg forces the network's internal representations to follow a diverse bell curve-like spread, an isotropic Gaussian distribution.
So it forces the data to be spread out.
Exactly. It demands that the latent vectors be spread out symmetrically in a high-dimensional space. If the network tries to cheat and collapse everything into one single point, SIGReg heavily penalizes it. It mathematically mandates diversity.
Okay, and correct me if I'm wrong, enforcing a complex distribution constraint in a massive high-dimensional space is usually notoriously difficult to compute.
Oh, it's usually intractable.
Right. Checking the spread across 192 dimensions at every single training step should be impossible for a single GPU.
It is computationally prohibitive, which is exactly why the older models use those messy 7-term workarounds. But the researchers found a brilliant shortcut using the Kramer-Wald theorem.
The Kramer-Wald theorem.
Right. Instead of trying to measure the distribution of the entire 192-dimensional space all at once, they project the data onto random 1-dimensional lines.
Okay.
And then they run a highly efficient empirical test, specifically the Epps pulley normality test, just on those 1D projections.
Wait, okay, let me unpack this for the listener. It's like trying to figure out if a really complex 3D sculpture is a perfect sphere, right?
Yeah, I like where this is going.
So
Yeah.
instead of building some crazy expensive 3D measuring tool to check the whole sculpture at once, you just shine a flashlight on it from a bunch of different random angles.
Yes.
And you just look at the 2D shadow it casts on the wall, or in this case, a 1D line. If every single shadow from every single random angle is a perfect circle, The theorem guarantees that the high-dimensional object has to be a perfect sphere.
That is a perfect analogy. You verify the complex high-dimensional geometry entirely through cheap, low-dimensional shadows.
Oh, that's so clever.
By testing multiple random 1D projections and making sure they follow a normal distribution, they mathematically guarantee that the entire high-dimensional latent space forms that isotropic Gaussian spread. No heavy computational overhead required.
Okay, but let me push back on the efficiency here for a second. The paper notes they use 1,024 random projection angles, right? Even if that EPS pulley test is lightweight on a single line, running 1,024 statistical tests from different angles per forward pass, doesn't that create a massive bottleneck? Doesn't that defeat the whole purpose of being efficient?
It's a totally valid concern if you're thinking about those operations happening sequentially, one after the other, but that's not how the hardware executes it.
Oh, it does it all at once?
It's exactly. Computing a covariance matrix in a high-dimensional space scales quadratically. It's slow. But a 1D projection scales linearly, and projecting a batch of vectors onto 1,024 random lines is really just a single dot product operation.
Ah, so it's not a loop of 1,024 individual tests.
Not at all. The whole thing is completely vectorized. It executes as one large matrix multiplication. The GPU handles all 1,024 projections natively in parallel in literally a fraction of a millisecond.
Wow.
The computational overhead of SIGReg is practically zero compared to the neural network itself.
So they secure the mathematical rigor of a complex test for the price of a basic math operation. And because the map is so clean, it fixes the tuning nightmare, right?
Completely. It reduces the tunable hyperparameters from PLDM 6 or 7 down to exactly 1, just one single coefficient they call lambda.
Just lambda.
Right. Lambda just controls how aggressively you want to enforce the Gaussian spread versus how much you care about the prediction loss. You don't need a massive grid search. You just dial it in using a simple logarithmic bisection search. It makes training exceptionally stable.
That is an incredibly elegant fix. But, mathematical elegance doesn't always translate to the real world.
Yeah.
When you actually drop this AI into a physics environment and ask it to control a robotic arm or navigate a maze, does it actually perform?
The empirical benchmarks are where LeWM really shines.
Yeah.
It's not just a neat math trick. First off, let's talk about its size. LeWM is incredibly compact. It's running on just 15 million parameters.
15 million. That's tiny compared to foundation models.
It is highly compressed. And because it's so small, and because it uses roughly 200 times fewer tokens than models like Diner WM, the planning speed is off the charts. LeWM plans 48 times faster.
Wait, really? 48 times faster?
Yeah. If you ask Dino WM to plan a trajectory for a robot, the inference takes about 47 seconds.
Which is an eternity in robotics.
Exactly. LeWM computes that exact same plan in less than 1 second, 0.98 seconds to be exact. It crosses that critical threshold into real-time sub-second reactivity.
That's amazing. But what about accuracy? Does moving 48 times faster mean it hallucinates the physics?
No, it actually beats the older models. On the push-TIA benchmark, which is a 2D task where an agent pushes a block into a specific zone, LeWM beats PLDM with an 18% higher success rate. And on OG BenchCube, which is a much harder 3D robotic arm task, it is highly competitive.
Okay, but I was looking at the performance data for the two-room navigation task, and LeWM actually performed worse than the legacy models there.
Yes.
Why did this super smart, mathematically elegant model fail at literally the simplest game on the board, just moving from one room to another?
It's a fascinating limitation, actually. It exposes the catch with the SIGReg constraint. The two-room environment didn't fail despite being simple. It failed because it's too simple.
What do you mean?
The data set for two-room has very low intrinsic dimensionality. It's just a dot moving on a flat XY plane. But remember, SIGReg aggressively demands that the AI's internal representations spread out to fill a complex 192-dimensional Gaussian distribution.
Oh, so it's forcing the AI to see complexity where there isn't any.
Exactly. It's like trying to stretch a tiny little piece of dough over a massive, extra-large pizza pan.
It just tears the dough.
Right, it tears the representation. The encoder struggles to artificially inflate that simple 2D data to match the massive 192-dimensional demand. But the moment you put it in a visually rich, dynamic 3D environment, the intrinsic complexity matches the math, and it thrives.
That makes total sense. Okay, so we know it can move a robotic arm and push a block.
Yeah.
But here's the real question. Does LeWM actually understand the physics of its environment? Or is it just mindlessly crunching numbers to maximize a score. How do you even test the physical intuition of a computer?
That is the big question, and the researchers used 3 really incredible tests to quantify its physical understanding.
Okay, what was the first one?
First, they used probing. They proved that you can accurately extract the exact X and Y coordinates of an agent or the exact angle of a block directly from LeWM's latent space.
So it's building its own internal coordinate system from scratch.
Exactly. It's not just memorizing pixels. Second, they tested something called temporal latent path straightening.
That sounds intense. What is that?
It's actually a phenomenon from neuroscience. As biological brains learn to predict motion, the neural representations of those consecutive movements become increasingly straight lines in our brains. And LeWM does this exact same thing.
As an emergent behavior.
Purely emergent. As it learns physics over time, its predictive trajectories naturally straighten out.
Wow, okay. But the third test is the one I really loved. The violation of expectation framework, or VOE.
Yes, the VO test is brilliant.
Because here's where it gets really interesting for the listener.
Yeah.
This VOE framework is literally how child psychologists test babies. Like, they'll show a baby a toy train going into a tunnel, and then they'll secretly pull a completely different toy out the other side. And if the baby looks surprised, it proves they understand object permanence. They know the train should still be a train.
Right. It tests their internal model of reality without needing them to speak.
So how did they apply this baby test to the AI?
They fed LeWM sequences of a moving block, let it predict where the block was going, and then they tricked it. First, they just changed the color of the block mid-movement.
And what did the AI do?
It didn't really care. Its prediction error, its mathematical surprise, stayed low. Because statistically, a color change is weird, but it doesn't violate the actual laws of kinematics. The momentum and mass are the same.
Makes sense.
But then for the second trick, they teleported the block.
Oh.
Mid-movement, the block instantly vanished and reappeared somewhere else on the screen. A total violation of the continuity of physics.
Huh.
LeWM's prediction error spiked massively. The math essentially gasped in surprise.
That is amazing.
Because it knows objects don't teleport. It developed a rigid baseline expectation of physical continuity entirely on its own.
That is just incredible. Okay, let's summarize this journey for everyone listening. We started with a trap of representation collapse, where lazy AI just maps the universe to a single static point to pass the test.
Right.
And we saw how previous models either got bogged down in messy 7-term math, or they just froze the AI's perception completely.
And LeWM fixes all of that with SIGReg. By using that brilliant 2-term loss and the Cramer-Wald theorem, it forces the AI to build a rich, diverse world model without needing a supercomputer.
Which means anyone with a single standard GPU can train an AI that learns the laws of physics, plans 48 times faster than massive foundation models, and actually acts surprised when you teleport a block.
All entirely within a compressed mathematical latent space. It never explicitly reconstructs the visual pixels of reality.
Which is just wild to think about.
It really is. And I think it leaves us with one final, really provocative thought to ponder.
Why?
Well, LeWM develops this profound understanding of physics, right? It knows when objects move unnaturally or teleport, but it does this entirely through abstract math. If a machine can develop a human-like surprise at broken physics without ever actually perceiving the universe the way humans do, does a true artificial general intelligence even need to see the world like us to understand it perfectly?
Wow. Yeah, maybe our pixel-by-pixel visual way of seeing things is just one limited way to interpret reality.
Exactly. Math might be the clearer lens.
Something to think about next time you're navigating your morning commute, predicting the traffic. You're just calculating paths in your own biological latent space.
And now the AI is doing it too, just 48 times faster.
Very true. Well, thanks everyone for joining us on this deep dive. We'll catch you next time.